All right, can you hear me? I'd like to thank the organizers for inviting me here today to pay our respects to Dick and celebrate his many contributions to our field. Of course, as Dick's PhD student, I learned a great deal about research from Dick. And I think Sanjeev and Prabhakar captured well Dick's philosophy of concreteness and utility. And I think I've taken that with me throughout my career, even through a sort of midlife crisis where I made a big change and started working on quantum computation, which arguably isn't the most practical of choices. I think I've taken that philosophy with me. And I also learned a great deal from Dick about teaching. And to this day, whenever I am preparing a lecture, I have in my mind that gold standard that Dick set for us of these beautiful, crisp, and clear lectures. And I am still striving to reach that gold standard today. I'm getting better all the time, but I'm still striving for it. And of course, I think we're all here today partly because Dick's many contributions have really shaped what our field is today. So even though some of us may not have had the pleasure of working directly with Dick or taking his classes, we're really all the beneficiaries of his enormous influence. So speaking of which, I'm going to start with, let's turn this on. I'm going to start with something that we all know, and that we've come to understand the class NP as the class of problems for which a yes instance can be verified deterministically given the proper witness to it. And of course, our first NP-complete problem was an important first step, but really a complexity class derives its importance from the significance of the problems that are complete for that class. So an idea which Dick pioneered. And so it was really when Dick showed those first 21 combinatorial problems that are complete that we understood exactly the central role that this idea would play in our field. And since then, of course, the rest is history. Literally thousands of problems have followed suit from every branch of engineering and science. So when Alexei Kitaev introduced the class QMA, it really felt like for those of us in computer science, it was really a very natural generalization of an idea that was already very fundamental for us. So what's the difference between the two complexity classes? Well, I've replaced my classical string that serves as the witness now with a quantum state. It's stored in a quantum register. And now the verification process is carried out by a quantum computation, polynomial time quantum computation. And the NP is replaced by the class Merlin-Arthur because quantum computation by its very nature has two-sided error to it. So this verification process is necessarily going to have two-sided error. So Kitaev, when he first introduced the class, also gave us our first QMA complete problem, which is the local Hamiltonian problem. So I'm going to tell you a little bit about that problem to define it. OK, so in local Hamiltonian, we have a set of particles. I've drawn them here as qubits. So they can be up or down in the 0-1 state or any quantum superposition of the two, but they could be potentially finite dimensional particles. And constant size clusters of these particles interact in some way. So let's just focus for a second on a particular little cluster. I've shown a cluster of 3 qubits, okay? So the dimension of this space is 8, 2 to the 3. And the energy interaction of these 3 little qubits is described by a linear operator. And if I diagonalize this matrix, a basic postulate of quantum mechanics says, if this is my little 3-cubic system, and I measure the energy of the system, then afterwards, the result of the energy that I'm going to get is one of the eigenvalues of this matrix. And after the measurement, the state is going to be in a quantum superposition that corresponds to the eigenvector corresponding to that eigenvalue. Okay, so this is one of the basic postulates. I've shown here an energy in the middle of the spectrum, but here's the ground energy, the lowest possible energy that I could get. So this is the lowest possible energy of my little system. And the corresponding vector is the ground state, the lowest possible energy state that it can be in. Okay? So now I don't just have 3 little qubits. I have a whole bunch of them. Okay? And clusters are interacting. So I have a number of constant size clusters and their energy interaction defined, okay? And the Hamiltonian is the sum of all these little local terms. And the goal is to find the global quantum state that minimizes the total energy of my system, okay? So it's an eigenvalue problem. The Hamiltonian has a very succinct representation because it's the sum of local terms. But if I expand it out, say I have n qubits in my system, it's really a 2 to the n by 2 to the n matrix. So it's an eigenvalue, eigenvector problem on a really large matrix. Okay? And if I want to phrase this as a decision problem, I'm asking, is there energy less than some threshold, or is it bigger than some threshold? And since these are real numbers, we have to pay a little attention to precision. I'm given some promise gap, which is 1 over polynomial in the size of my quantum system. All right. So if it just so happens that each one of these local terms is already diagonalized in the 0, 1 basis, this is exactly the constraint satisfaction problem. So each of those diagonal entries tells me the cost of those 3 bits being in that configuration, okay? And the goal is to find the global classical state that minimizes the total cost, okay? So it's a very natural generalization of a problem that we're quite familiar with already, okay? But we don't just make a quantum version of something for the sake of making a quantum version of it. As Dick showed us back in '72, NP is important because of the importance of the problems that are complete for the class. And similarly, the same case is true for local Hamiltonian. Now, QMA doesn't have the same rich array of complete problems that NP has. But the local Hamiltonian problem itself is a really central problem in condensed matter physics. And if you look at a lot of the work that takes place in computational physics, looking at quantum many-body systems, to some degree, a lot of this activity is focused on finding ground states and ground energies, okay? So instead of just telling this to you, I want to give you a particular example to give you a little bit of a flavor for the kinds of questions that are of interest there. So I picked this particular example because one of the authors, Steve White, is a colleague of mine in the physics department at UC Irvine. And his office is a few buildings down, and he was willing to sit with me and explain his paper to me. So that's how I chose this particular example. So we have a beautiful lattice structure here called the Kagame lattice, okay? And sitting at the vertices of this lattice are qubits, 0, 1 quantum variables. And pairs of qubits interact. Wherever there's an edge between 2 qubits, there's an interaction, okay? And the physics of this interaction is described by this little 4x4 matrix. It's a very well-studied model called the Heisenberg antiferromagnetic. So if you notice, for example, on the diagonal, the 0, 0, 1, 1 have a positive entry, showing that there's an energy penalty for spins being aligned, okay? And a negative for the 0, 1, 1, 0, showing that the system tends to want to be anti-aligned, okay? And the off-diagonal terms sort of demonstrate movement, indicating that the ground state is going to be some quantum superposition of the two, okay? So it's a frustrated system. We have, odd length cycles, and things want to be anti-aligned, okay? So the basic question that they were asking in their paper, and they're interested in the behavior of this model on an infinite 2D lattice, okay? So the basic question that they wanted to answer is, what's the structure of the ground state? So it's essentially a local Hamiltonian problem, as I've described it. So one possibility that it's a valence bond crystal, and I showed little clusters of 2, but a valence bond crystal are clusters, are periodic pattern of clusters of qubits that are locally entangled but not entangled with each other. Okay, so there's a broken symmetry. Alternatively, is it a spin liquid? And a spin liquid is a kind of a special state of matter that's not completely well understood. But if you do any measurement on a spin liquid, it appears completely disordered, much like a liquid, so there's no broken symmetries in the state. However, there's believed to be a lot of quantum structure in between, underneath that we don't completely understand. So for example, it's conjectured that these are created by quantum superpositions of different valence bond structures that sort of washes away the symmetry, okay? It's a state of matter that's not very well understood, and they're of particular interest for various reasons. One of the reasons is that the low-lying excited states of these systems exhibit very interesting physics. So these low-level excited states, the whole collection of particles are best mathematically described as weakly interacting quasi-particles. And these particles have interesting physics that you don't normally see. So they can have fractional charges and different statistics. So there was a while where it was conjectured that spin liquids are important for high temperature superconductors. Alexei Kitaev has proposed a model of quantum computation which would use these quasi-particles to actually compute in low-lying states. And it's believed that this might be a more stable substrate for a quantum computer. So regardless of the applications, it seems to be an important feature of physics that's not well understood, and people are trying to understand it better. And it's interesting because it seems that 2 dimensions seems to be a sweet spot of complexity, and you see more of this interesting physics in the 2-dimensional models. So at any rate, so Steve writes in his paper, a key problem in searching for spin liquids in 2D models is that there's no exact or nearly exact analytical or computational methods to solve infinite 2D quantum lattice systems. So there's really not successful heuristics in this area. So it's a reasonable question. If you had a quantum computer, would it help you solve this problem? Okay? And I guess more generally, we believe that if we could build a quantum computer, that it would be useful for problems in the physical sciences in which you have to model or simulate quantum phenomena, things in material science, problems from computational chemistry or condensed matter physics. And it would be very nice to flesh out this agenda a little bit more because we don't really understand exactly how a quantum computer could help in this department. So I'm going to tell you a little bit about the state of the art. Most of it is hardness results, but there are a few glimmers of positive hope in there. So here's a picture that you're all familiar with. Here's the famous tableau showing that the computation of a Turing machine can be used, an instance of satisfiability can be used to capture the computation of a Turing machine. Okay? And each row, of course, is a state of the Turing machine. Time goes from top to bottom. And our instance of Boolean satisfiability each has, there are these little pieces of finite logic that each enforce the fact that if this is going to be an accepting, if it's a satisfying assignment, that it has to accurately model the progress of the Turing machine. Okay, so we know this well. And in QMA, the picture is very similar. Okay, but instead of having this 2D tableau structure, we're showing a static object, which is a quantum state, that represents a dynamic quantum computation. And now each step of the computation is expressed in quantum superposition. So this computation state was first suggested by Feynman in '86. So this would be akin to the satisfying assignment for the tableau. So each particular state in my superposition represents one step in a quantum circuit, say, okay? And they're all expressed in quantum superposition. The clock is expressed in unary and sort of keeps the different slices of the time steps in different parts of the Hilbert space. So the Hamiltonian is a sum of local terms that enforces that a low energy state corresponds in this way to a valid accepting computation of my quantum verifier, okay? And so how much logic do I need to actually enforce this? Well, it turns out that operations on 5 qubits are sufficient. So I need to, some of the qubits on the right are the computation qubits. The qubits on the left are the clock, and it says, well, if my clock is in state I, then I need to implement the ith gate, okay? So the theorem that Kitaev proved is that 5 local Hamiltonian is QMA complete. So this is, in some ways, exactly the picture that Sanjeev showed us this morning, where you have a family of practical problems that you want to solve. We've drawn a big circle around it of a very general problem, and we've shown something else to be difficult in that class. Okay? So a lot of the subsequent results are the process of sort of tightening this circle around the family of problems that we really want to solve. Okay, so the first step, if you look at this picture here, it's called local Hamiltonian, but there's no physical locality happening here at all. The qubits are scattered, and I'm just picking 5 of them and operating on them. Okay, so the first step is actually to talk about these particles being laid out in some finite dimensional space. So the first step was to show that even if my particles are laid out on a 2D grid and I only have pairwise interactions, it's still a hard problem. Okay? And the idea is it's still the same quantum superposition state, the ground state. The particles are now finite dimensional particles. And the clock and the control is sort of now distributed through my system. So each particle encodes part of the computation that's going on and part of the control that's happening. Okay? This was then improved to actually qubits in 2 dimensions, where each of these finite particles is now replaced by a gadget on qubits. And then finally, even in 1 dimensions, even on a line, the problem is difficult. So this was interesting for a couple reasons and a little bit surprising. First of all, this differs from the classical picture, because we know that constraint satisfaction in 2D is hard, and on a line you can just use dynamic programming for it. So, and the thing that we can get away with in quantum is that there's a lot of rich information in a quantum superposition. Okay, so we're actually still encoding a lot in that quantum superposition. Another reason why it was somewhat surprising is that in 2D, physicists, their heuristics are still quite unsuccessful on 2D systems, but were very successful in 1D. So for the physicists, 1D was solved, and it wasn't problematic. So it's a little surprising that it was still difficult. And it was later explained partly by the fact that if your Hamiltonian has a gap between the lowest and the next highest excited state, you actually can solve the problem in polynomial time. So that helps to understand why heuristically physicists were having better success with these systems. Okay, another way in which these vary dramatically from the Kagome lattice that Steve and his colleagues were trying to solve is that this is obviously a carefully engineered instances that we're showing are difficult. So if you look at the local constraint between particle I minus 1 and I, it's completely different than the local constraint between particle I and I plus 1. Because these are being used to actually implement the gates of a circuit. Okay, so we're saying, implement this gate here, that gate here. So it's a very carefully engineered construction. So what about translationally invariant systems? So we don't even know exactly yet how to define, even talk about a family complexity classes here. But here's the definition that helps us get a little closer to it. So I'm going to define as a part of my problem description the dimension of the particle and the interaction term. So that's given as part of the problem, just like the physicist would study, Heisenberg model on a Kagome lattice. Okay, that's part of the problem. The input is just an integer. Okay, so that's all you have in the input. And then you ask, if I were to have a line of particles and apply this term on each pair, and the line has n particles in it, what's the ground energy of the system? Okay, so this is sort of captures this translationally invariant feature. Okay, and as it turns out, this is also hard. Okay, now I have QMA exp, and the reason I have exp is that the witnesses and the verification process is exponentially long because now my input is exponentially shorter because I'm encoding it in binary. So I'm interested in things that are polynomial in the size of the system. Okay, so it appears that this is also hard. Now, I've drawn here this schematic, but really this is a better picture of what it looks like because the dimension of these particles is constant, but it's really only a constant that a theoretician would love. It's really a big number. So this ain't no qubits, or we're far from the sort of more practical models that the physicists are interested in. So you could ask, well, what about natural quantum models? And what can you say about the hardness of those, which is really kind of what we're getting at. At the other end of the spectrum, there are results that actually look at very natural, well-studied physical terms. So I'm defining the term between two particles to be one of the most simple models that physicists study. And if I allow my graph structure now to be more complex, then it's still hard. So you can encode the quantum circuit itself in the structure of the graph, and it's difficult. Okay? So we have hard graphs, but simple interaction terms, simple graphs, hard interaction terms, and we'd really like to know what's sitting in between. Okay? So everything here has been bad news so far. So is there anything positive we can say? A few things we can. So one of the early results in quantum algorithms is that you can actually simulate the time dynamics of a quantum system using a quantum computer. So we know from another postulate of quantum mechanics is that the time evolution is governed by Schrodinger's equation, and this is that same energy Hamiltonian here. And I've shown the solution here for a time-independent Hamiltonian that doesn't change. And if it's local, then given a starting state, you can actually estimate this time evolution. It still leaves us with the problem of finding a natural or physical starting state in all of Hilbert space. So this still remains a problem. And I've also only focused on ground states. Okay, so in higher temperatures, the state of our system is sitting in a probability distribution over states governed by the Gibbs distribution. So the probability of some state is proportional to this exponential function. And we have the temperature T, which represents temperature. So in high temperatures, this converges to a totally uniform distribution. In very low temperatures, the energy is emphasized and it's peaked at the low energy states. But we'd like to be able to sample from this Gibbs distribution in between, okay? And of course, there's been a lot of work in this community looking at classical models like the Ising model and understanding the convergence rate of Markov chains. So in the physics community, a go-to algorithm for this is widely used for classical models, is the Metropolis algorithm, in which you're sitting at a state, you tweak it a little bit to get another state, and then you decide to go to that state with some fixed probability proportional to exponential in the difference of the two energies. So this has been very successful, used heuristically within the physics community, as well as analyzed within our community as well for classical models. Now, what about implementing that using a quantum computer? So here, we're doing exactly the same thing. We're trying to find a classical distribution governed by Gibbs, but the underlying states that we're walking on are quantum states. Okay, so they're these quantum eigenvectors of our system. Okay, so just to store a single state where we're sitting, in principle, could require a quantum register and a quantum computer just to represent the object itself. And so we'd like to implement exactly that same algorithm. We'd like to be able to sitting in a state, tweak it, and make the decision about whether to go or not. And we don't know much about convergence, but even implementing this algorithm is problematic on a quantum computer. And the reason is you're sitting at a state, you tweak it in some way, and now you have some quantum superposition of where you might go to if you decide to take this step. In order to decide whether you take the step, you have to perform a quantum measurement of some kind. Okay? And quantum computation is reversible except when you do a measurement. Okay, so the main contribution of this paper is the fact that they give a way to actually reverse, if you decide to reject the move, how you go back. And they use a beautiful trick by Marriott and Watrous of iteratively sampling that gets you back to your original state. So the accomplishment here is just that you can implement Metropolis algorithm, and this does converge to the Gibbs state that you'd like to be able to sample from, but we know almost nothing about convergence. Okay, so it's really wide open whether this is actually efficient and for which systems it's efficient. So in terms of provable bonds, we know almost nothing. But this could prove to be a useful heuristic, as it has in the classical case in the quantum community. So we've spent the last few decades, thanks to Dick, since 1972, coping with NP completeness. And I suggest that we spend at least part of the future decades coping with QMA completeness. So thank you, and happy birthday.
Any questions?
Well, in this, I think this is addressing your point, but in the quantum Metropolis algorithm paper, they make this claim, well, this algorithm will converge quickly whenever nature does. I mean, there's not really much of a formal basis for that, but it's possible that there are natural systems where it doesn't actually converge. So it's not clear that we actually get to the true Gibbs distribution. You mean actual physical experiment and then comparing it with the actual, presumably. We need the quantum computer first, though, I guess.
Any other questions?
Right.
Thank you.
Thank you.